F, and I also need to define for C but maybe yeah, let's take a 5-minute break and continue after. Yes, so yeah, this in fact implies this is G acyclic. Yeah, one can prove this using that relation between the transversality and acyclicity. Okay, so now let me define this one. Yeah. So x say as in 4.4. So first h. So I introduce that terminology. So this is also as in 4.4. Then we say this pair is C acyclic over S. And this condition is rather complicated. So we consider pullback times pullback of the everything, and its intersection with the kernel. So up to here, it's similar to the definition of acyclicity. So on this side, we just take pullback, and on the second factor, I take the whole thing here, and I consider the intersection with the kernel. So this, and in the geometric case, we just require that this intersection is the kernel of the section. But here, I require this to be a subset of the kernel. So I'm just copying the same thing here. But this goes to the pullback of the fiber product, and I require this inclusion. So the idea is somehow similar to this F definition for F, but it's less straightforward, so it's not easy to explain. But one point is that if W is smooth over this fiber product, then this condition is trivially satisfied.
Okay, so this is one dimension. So when Y, you assume Y is smooth over.
Yeah, Y is smooth over S.
So this kernel is one-dimensional sub-bundle, yes?
Yeah, yes.
Okay.
Yeah. And we say this C is S saturated if it is stable under the action of the pullback of this. So this is closed conical subset of the Frobenius Witt cotangent band. So we have natural map from here to there, and we just saturated this condition that it is stable under the action of this line bundle. So let me tell you two examples. The first is, so suppose HF is C acyclic, and Y2S is C prime acyclic. Then we have this product motion. So this is the sum of the two pullbacks transversal. And second property is, so assume H is C transversal, and at the second motion, I just take structural motion to S. Then if this C is S saturated, C is S saturated, then this pair is C acyclic over S. So once you get to this definition, this is rather elementary. So I will just skip this. And using these properties, I can give you the relation between abstract one and relative one. But to prove the relation, I need one property which I don't know how to prove. So suppose we have two sheaves on X, and assume F is micro-supported on C and G is micro-supported on C prime. And so if the support of the intersection is empty, so if they are micro-supported on a different direction, then the tensor product is micro-supported on the sum.
The sum, this means the sum of vectors taking the closure, okay.
Yeah.
And when you take the sum up there, do you take the closure also?
In this case, by this assumption, they are in the different direction. So I think it's okay. I don't need to take closure.
Okay.
By the way, this is some transversal over S, right?
No, transversality there is no S. Acyclicity you have relative. For the acyclicity you need a base, but the transversality there is no base. So more weakly, yeah. So this is the case where we have only one scheme, but now we have f on x and g on y, and y is smooth over s, and yeah, again f is micro supported on c, and g is micro supported on c prime. Then this external product is micro supported on the sum So this is a special case of that one.
So you have the expectation in the geometric case?
Yeah. In geometric case, this is proved. Yes. Yeah. So to statement. So assume f is micro supported on C. So this is an abstract one. And if this expression holds, then f is S micro supported on C. And the second one, so suppose f is S micro supported on C, and then if C is S saturated, then f is micro supported on C. So the first statement says that absolute one implies the relative one, but I need to assume this property. And the second one says that the relative one implies absolute one, but I need this condition, saturated.
Why you don't need the closure in more weakly? Why you don't need to take the closure of the sum?
Sorry. Yeah, I need to, because I forgot to say one thing. So this C prime should be S acyclic. Yeah, thank you.
Okay, so this means that it is not, it is so, okay.
Yeah. Thank you. Okay, so let's prove this. So we want to, so we assume F is microsupported on C, and we want to show that F is S microsupported on C. So,
Yeah. Ah, okay.
Stable by action of the line. Just the line is maybe.
yeah.
Okay, stable and then the action.
Okay. Yeah. So the conclusion is it's S microsupported on C. So we need to test by H and F, which is C acyclic over S. And so assume. And we want to show that HF is F acyclic over S. Okay, so we take G on Y, which is S acyclic, and then this acyclicity means that this motion so we want to show that this is this transversal. But this sheaf is by expectation, so this is micro-supported on this this sum. And yeah, by this property, if yeah, this pair is this.
C is microsupported where?
Hmm?
C, the same C or?
Sorry, this is C prime, and so S acyclic means that this is micro-supported on C prime, which is S acyclic. Which is such that Y to S is C prime acyclic. Yeah, thank you. So G is S acyclic. That means G is micro-supported on C, this on such C prime. And by that example, this motion is this transversal. And by expectation, this external product is micro-supported on this sum.
So you have to go from tensor product to external product.
This is external, yeah.
And the tensor product, the assumption is about the tensor product.
Yeah, this yeah. So this more weakly.
So on the more weakly expectation.
Yeah.
No, okay, but the more weakly is including this assumption on cyclicity of product.
He's using just the more weakly.
Only the more weakly.
Yeah.
But the more weakly comes from the tensor, doing the tensor product on.
Yeah. Yeah, if you apply this to the pullback, then we get to this property.
Okay, so you have to know compatibility with. Okay, but you have this in your theory. Okay.
Yeah. Okay, so using that expectation and that property, we have this first one. And second one, so assume so now we want to prove absolute one. So we just take one more sum and assume transversality. Then we want to this H is F transversal. Okay, so in this case, we take F to be the structure most smooth S. Then by this and the assumption that so we assume that S is C is S saturated. Then HF is this pair is C acyclic over S. So this yeah, then so we can take as G, we can just take constant sheaf. Then this implies that this H and F. So this map is this transversal, and this is what we want. Okay, so we have this implication. So we don't know the existence of the singular support, but if they exist, this lemma implies that if SS exists, and also relative version. So I didn't define relative version, but we defined the micro support, relative micro support. So we can, as usual, we can define relative singular support as the smallest one, and relative saturated singular support as the smallest saturated one, on which F is micro supported on S micro supported on C. So SS and if they exist, this lemma says that we have this inclusion. So this means that relative. So this is the correct one. So the relative one can be too small, and the saturated one can be too big, but the difference is just one dimension, because saturation means that it's close under the line action of line bundle. And moreover, if this motion is 0, then the condition is trivial, so everything will be saturated. So if X is far from smooth over S, then these two should coincide, and these all three must be equal. Now I can state a theorem. So I can't say anything about these two, but the last one, so to prove this, I can, so the proof is same as Beilinson. So I can reduce to the case to projective space over S. And if your X is smooth, and if we consider only saturated one, then so instead of working this cotangent band, Frobenius Witt cotangent band, we can also work with the Frobenius pullback of cotangent band restricted to characteristic P fiber. So because if X is smooth over S, then we have this exact sequence. And if we assume this saturatedness condition, so that means it's stable under the action here. So the saturated closed conical to consider saturated closed conical subset here means that you just consider closed conical subset here. And this Frobenius is homeomorphism, so you can ignore this. Then, then you can literally copy the argument of Beilinson to prove the existence. Okay. So in the remaining time.
So but you still have expectation 4.8. So because you don't prove completely expectation 4.8, do you know that there is a smallest saturated conical subset so that F is micro-supported? You do it with S micro-supported, and in the lemma you need expectation 4.8.
Yeah.
So this means that to prove that there is a smallest saturated conical subset on which F is micro-supported, you need some expectation 4.8, or not?
Yeah. In the theorem, you don't use the expectation.
In the theorem, I only work with saturated ones. So this theorem is independent of this lemma. So I don't.
Yes. Okay.
Yeah. So this is only the existence of this. So I can't say anything about the existence of these two.
So you don't say that there is a smallest saturated conical subset on which F is micro-supported without S, just because of this expectation. So you don't say this.
Yeah. Okay, so the remaining time, let me try to prove this proposition. Thank you. So this is essentially Braverman. Gaitsgory. Okay, let me recall the statement. So F is most of finite type. Over excellent regular Noetherian scheme. Okay, and F is sheaf on X, and assume X to S is F acyclic, universally F acyclic, and Y is smooth. Then the following are equivalent. So the first one is this F is F acyclic, and the second one is for any sheaf on Y, this graph motion is transversal. Okay. Okay, let me try to prove this. So in second condition, we may consider only G to be I star of L, where I is immersion and L is locally constant. So by some depth search, we need only consider these G. And further, this V is regular. Okay, now we consider a Cartesian diagram. X cross Sy. So W is X cross YV. So this is our most gamma, and let's call this gamma prime, and they are just projections. Okay. Then I already let me also recall another proposition. This this is you can find in SJ 4.5. or book of Frobenius, F of finite type, and F sheaf on. Maybe I don't need a finite type. Then the following are equivalent. F is F acyclic. So for in every Cartesian diagram, such that I is imagine, and for any G on V, this conical motion H star F then is star large G is our isomorphism.
That's why H apple star doesn't look.
Sorry?
You wrote twice H apple star.
Yeah. Sorry. Yes. Yeah, thank you. Okay. So we have this proposition. And here also, this G, so we can also assume here G can be locally constant. And this condition so with the notation here, so we can write this as gamma star of F external product of I star of L. So I replace this G by L. And this one, similarly, so H star of gamma prime star of F external L. So the second condition is that this is an isomorphism. Okay. So we want to prove that these two are equivalent. But now using that interpretation, I can reformulate it as follows. The first one is the acyclicity, so it rephrase like this. So for every immersion and L on V locally constant, the most there, so this gamma star, gamma star going to H star gamma prime star this is our solution. So this is the interpretation of the first one. And for the second one, so similarly, and the immersion of regular scheme. Yeah, for the second one, it's also the same thing. So immersion and locally constant sheaf on V. Then the transversality, let me just write down the transversality. So gamma star of F tensor gamma sheaf of lambda is gamma sheaf of this one. Is isomorphism. So we want to prove the equivalence of these two. Okay, so yeah, and this is the kind of C. Now I like a commutative diagram. So the upper line is just this one. Okay. And here we have this one. So I'm going to this one, but with tensor with pullback of that one, and take direct image. So this is almost a twist of this. And then from here to there, and if you go from here to gamma prime sheaf of lambda, then we have C for gamma prime. So we can go to go there. So this is almost H star of C for gamma prime. So this is C for gamma. And here is the base change isomorphism. So we have this is. So this is isomorphism by proper base change. And we need to check, of course, check the commutativity, but I skip this. So we have this isomorphism. Okay, so we want to show that isomorphism here is equivalent to isomorphism there, and the second map is here, and the vertical map here is almost the same. So this is isomorphism is equivalent to, so by this regularity, this immersion is regular immersion. So this is locally constant. So we can ignore this part, and this is isomorphism if and only if that is isomorphism. Yeah. So if this was isomorphism, then they clearly we get the equivalence. But we don't know this, so we have to work a little bit more. So I have to give a name.
So start of C gamma 1.
Sorry?
It's almost the start of C gamma 1. This is okay.
Yeah. I always put this star somewhere wrong. Yes. Okay. Okay, so let me call. So in my note, this diagram is 3.4, and this motion is 3.3, and this is 3.2, and this 3.5 is this motion before taking H star. So H is gamma prime star F tensile H star gamma shriek lambda going to okay. And let me call this A. Okay, so the claim is the following equivalent. The first one is that 3.5 and that A are isomorphism. Second one is 3.3 is isomorphism. And the last one is all arrows in 3.4 isolation. So we claim this. Okay. Let's prove this. So 3.5 is isomorphism. So because we assume this as isomorphism before taking H star, so after taking H star, so of course we have isomorphism here. Okay. And we also assume that this A is isomorphism. So yeah, and the diagram is commutative. So this implies 3. Okay. And second implies the first. So 3.3 is isomorphism. So we assume this is isomorphism. And we know that that is isomorphism. So that means this composition is isomorphism. Okay. But this H is the base change of I. So if our I is immersion, so H is also immersion. So if this is the isomorphism, then by taking the adjoint, I can move this H star, H lower star as H upper star here, and still we get isomorphism. So I said H upper star of this is isomorphic to that one. And this exactly means 3.5 is isomorphism. So let me write. So second, by assumption, this composition is isomorphism. And by adjunction, 3.5 is isomorphism. So 3.5 is isomorphism, then this is isomorphism. And by our assumption, that and that, they are isomorphism. So, yeah, so A is also isomorphism. And yeah, then 1, 2, 1, 1, 3, 3, 2. Yeah, so we need to have this, show this, but this is obvious. Okay, now, so they are equivalent. So we have this 2 implies 1. So 2 implies 1 means so 2 says that 3.3 is isomorphism. Then this A is isomorphism, and A is isomorphism means this is isomorphism. So this always already shows that 2 prime implies 1 prime. Okay, so we want to our remaining task is to show this implication. Okay, so assume 1 prime. And we want to show that 3.3 is isomorphism. Yeah, 3.3 is isomorphism. But so assuming one, so this means that A is isomorphism. And we already have this equivalence. So to prove 3.3, so this is enough to show that enough to show 3.3 is enough to show 3.5. Okay. So first we consider the case where I is open immersion and L is constant sheaf. So in this case, yeah. So in this case, so why is this? So by our assumption, so why is it smooth? So this base change is smooth. So this gamma is a section of smooth motion. So and our sheaf here is f is here, and we just take pullback of f. So by the transitivity of transversality, this gamma of transversality gamma is transversal. Here, so this smooth monster is F transversal because of Poincare duality. So gamma is a transversal means that this upper line, this 3.3 is isomorphism.
You don't go through 3.5. You go directly to 3.3. You don't go through 3.5. You go directly to 3.5.
Yeah. Here it's okay, but the next one. Oh, sorry. The next one is I is closed immersion. And I is what? Sorry, L is so yeah. So this is argument. So I already out of time. So I just say that I use distinguished angle. So yeah, so we have closed immersion. So complement is open. So we can use the first one. The last one. So in general, yeah. So in general, so we want to show that yeah, so this is isomorphism. But this L is locally free. Sorry, locally constant. So that means that it's enough to prove this isomorphism for a single non-trivial locally constant sheaf. Yeah, and I is general, but so that so we can argue locally. So we may assume I is closed immersion, and so as I said, L can be any non-trivial locally constant sheaf. So, but this case is already proved, and this is a non-trivial locally constant sheaf, so it's done. Okay, thank you.
This you said that this is in one of your papers. This proof is in one of your papers.
Yeah, yes. Yeah, the most recent one.
The one on the okay.
Yeah.
So, excuse me. So in this I being open immersion and L being the case, that the above. So you improving 2' implies 1'. You show first you assume I is an open immersion and L is the constant sheaf. And what?
Yeah.
Yes. And you get 3.3 by the transitivity condition.
On 2 prime implies 1 prime or 1 prime implies 2 prime? What are you?
Sorry, 1 prime implies.
Okay.
Yes. And you used transitivity.
Yeah.
And what is the argument? So you said.
So I want to show that this is the transversal.
Yes.
And well, we know this is the transversal because it's smooth.
But the sheaf is the F tensor I lower star of lambda, right?
Yeah, in sheaf is this, so it's just pullback of F.
But use I is an open margin, right? So L is living on V, the open of Y, and you push it forward to Y.
This is the first case. We started by the first case, open immersion, and he said that we can assume L equal lambda. This is the first case.
L is living on V, right?
Yeah, V, but I is open margin, so yeah, maybe I was confused with V and Y. Yeah.
But you consider star push forward, right?
Huh?
You consider star push forward.
Push forward. This is yeah. Here it's everything is over V. So you.
You are proving 3.5.
Yeah.
Do you?
So first, let's take the technical part. Any questions?
And as usual, there will be notes on the web.
Yes. The full notes will be already on the full notes.
Yeah. I will put this. Yeah.
Okay.
Other questions?
Is it sometimes useful to interpret acyclicity as something being dualizable?
Sorry?
Sometimes is it useful to interpret acyclicity as dualizability sometimes? Or?
Dualizability. Yeah.
You go from one point to another, but there are also other ones like.
I didn't.
No, I don't know, but just in general, I mean, even in the whole picture, it's sometimes useful to.
Yeah, maybe, but I didn't go into it. Yeah.
So it seems that Wager has also problems to understand the proof.
In the QL.
The l-adiques, of course, the
So do you understand it in the l-adiques?
No, because several years ago there was some emails with Gaitsgory and there was this.
So what he said?
Can you explain the problem?
But the problem is that all the theory of l-adic sheaves are going to minor balls, and I mean this doesn't work in the l-adiques in the classical way of doing l-adic sheaves, which requires some. So it's not. So I thought it's nonsense in the l-adic, but I didn't know. Maybe now, of course, there's more mechanisms with very sophisticated things. But I'm not sure if how to.
So actually, the conclusion of the previous discussion is that it was.
No, there was in 2017 there was some discussion with Gates. This reference was given in some old email, and I looked at it and I did not. So I had the same impression, maybe roughly and now I didn't look at it recently, so I cannot say. And I don't remember now those arguments are kind of translation of what they do into. Is essentially the same as what they but I don't remember.
Yeah, I try to understand what they wrote.
Yeah, and also why excellent. Of course, excellent helps to make things sufficiently regular on some small, but it should not be and regular. This I don't.
So why excellent regular?
Because I want this V to be regular.
And this is useful for.
So Yeah, so by divisions, I want to take some arbitrary subschema and take it's open, then I want it to be regular.
Why?
Yeah, because I need to work with this acyclic.
Okay.
Okay. Other comments? If not, let's take Takeshi again.